for me to give a lecture that has the name of Charlemagne, because where I grew up, he was our emperor too. So we learned all of these stories about Charlemagne. Even when I grew up, there was a song in French about how going to school and so on. It was all the fault of Charlemagne, because he had made rules about compulsive mandatory education of youngsters. Okay, so I'm going to talk about work that I started to do with, on the one hand, computer scientists and geometers, and on the other hand, biologists, about 6 or 7 years ago. So, bones, teeth, and animation. It's joint work with, on the one hand, Jan Lippmann, who was my postdoc when we started this, and who's now an assistant professor at the Weizmann Institute in Israel. And I like that he is both an expert in computer graphics, but also a mathematician. I mean, what that means is in computer graphics, people have beautiful and very powerful algorithms. And many of them have some ad hoc nature in them. But what I really like about the work that he does is that it's always that he takes inspiration from differential geometry, from to build algorithms that make sense mathematically, and then also computation. In fact, I don't want to belittle things that are based just on algorithms. I think that whenever an algorithm works well, it works well for a reason. And so I always tell my students, if something turns well, it works really well, and we don't understand it yet, it's a challenge for us mathematicians. So it's also joint work with Dirk Boyer, who is a, you can see what he has on his knee is not a mathematical model. He's a biologist. He works in evolutionary anthropology. He does in biology old-fashioned biology, if you want. He works on morphology, so that's the study of the shape of the organism. I mean, in this case, he works mostly on skeletons. But so it's in the 19th century, that's what lots of biology, especially zoology, was about. You hear these stories about people who could recognize an animal from just seeing a fragment of bone because they had such a good knowledge of these days, there's much more advances and much more stories about molecular biology and genomic research. But if you really want to understand evolution, I mean, evolution is mediated via the genome. The genome is the mechanism by which some traits can be inherited. Well, we now have epigenetics as well, but the engine that does the pruning of all the possibilities that exist via the genome is the interaction between the organism, the phenome, and the environment. So if you really want to understand evolution, you should understand not just genomics, but also the morphology. And that's his point of view. And he's passionate about making that study as quantitative and as feasible by non-expert as genomic research is. And we'll come back to that. And it's also joined with Timur Gao, who was my first PhD student at Duke. He finished a few months ago. He's now, I'm fortunate in that for personal reasons he wanted to stay local, and that he's now staying with Daubechies and me as a postdoc. Okay, so I have these different elements in my title. So animation is one of them. So animation, well, three-dimensional animation relies on computer graphics. And computer graphics uses three-dimensional mesh models of objects. And in the very beginning, the very first object that in computer graphics was meshed like that was the teapot. And this is a very old, this is the very first meshing actually for the teapot. And it came as a challenge for a computer graphics person by his spouse, who said, why do you guys always have these funny objects with a hole And so this became, the teapot has become much fancier. This is a more recent version of the teapot rendered in its full glory. And it's become an in-joke in Pixar movies that there always is a teapot somewhere. You can try, we always make it we always look for it. It can be in some set of toys in the dollhouse and so on, but the teapot is there. So 3D meshes became much more sophisticated over the years, as you saw with the teapot. Here are two examples. One is a fanciful piece of architecture in some animation. The other is something that is a real object for manufacturing. The meshes themselves changed. Actually, here you see the transition between nerves, piecewise splines, that were used by Pixar in their first movies. Toy Story 1 is completely, all the characters are done in nerves. And then starting with a short Jerry's Game, in which you see the character on the right here, who also reappeared in Toy Story 2 as the toy doctor, they changed over to a different way of representing meshes. When you have nerve piecewise splines, you have to be very careful stitching at the edges in order for the surface if you animate it for it to stay stitched together and to behave in a normal way. And it turned out that was much harder than working with subdivision. In subdivision, what you do is you build your surfaces by taking a coarse mesh and then from the coarse points predicting intermediate points with the local rule, and you keep subdividing. And by changing the rule locally, you can change the smoothness. And so, for instance, in Jerry, his whole hand is one surface, even where you have the transition between the finger and the nail. That crease there is just a different, locally different subdivision rule. And so it was so much easier to animate that for Toy Story 2, even though they had already all the characters, Woody and Buzz Lightyear and so on, already modeled as nerves, they redid them in subdivision surfaces. All the movies since About the Life have been done as subdivision surfaces. That's a little aside. So there's a lot of interesting things about computer graphics in animated movies. But for the application to biology, I'm not thinking about the evolution of animated animals. I'm talking about real objects. So you can also take existing objects and scan them, and you can do that via something like LiDAR, or you can do it by projecting some bar patterns on the surface and take photographs from different angles, and that will give you information about the 3D. Now, however you do it, what you'll end up with is a point cloud. A point cloud where each point has coordinates in 3 dimensions, and you then have to extract a surface from that. So I'm going to assume now that that is well understood, because I'm not going to go into that, although there are issues there as well. So once you have that, you can triangulate, and you get the Loney triangulation, and that's well understood how to do that. And you have a surface mesh for your surface. Here's an example of an object on the left that was scanned. And then you have on the screen the virtual representation of that mesh rendered on the screen. And then on the right you have the object as it was milled. I mean, these days you might think more of 3D printing than milling, although for very nice precision we still are using milling. I mean, although that will no doubt change, and 10 years from now this will no longer be true. I think 3D printing will then achieve the same, at a reasonable price, the same precision as milling could before. Any case, once you have triangulated surfaces, what can you do with them? Well, you can edit them. I mean, and in animation, that's done, for instance, you can make this giraffe go by moving points at a coarse level, and then everything else at the final level moves with it. But when we're talking about real objects, there are also things that we really want to do. For instance, if I scan the same object twice, then I will have two meshings that represent the same surface. But they will be different, because it's highly unlikely that I find exactly the same things. So how, if I give you two meshes, are you going to recognize that this is the same surface? Or that they represent very similar objects? Or if they're not so similar, but there's a scale difference that quantify. I mean, in this case, actually, these two Volkswagens, it's not just a question of scale. It turns out that when they made these dinky toys for the first time, if they just scaled everything down, it didn't look right. The toy looks too long. For some reason, we think of it as more snouty, more short, compressed than it really is. And so, how would you, if you had the snouty one on the dinky toys and the real one, how would you recognize from the meshing that you have a difference in shape and not just in scale? So, in fact, even in animation, issues like this come up. I mean, how do people animate a humanoid figure? Well, they have the model for it, and then they know how to move things in the model. But how do they know how to make it move it so that it will look natural? Well, they typically have actors that they make go through movements, and they put at key reference points, they put markers on the actors. These markers that they follow, they know their XYZ coordinates, and then with these markers, they can then transfer each reference point to the other model, and they can make the animation move. So we want to be able to recognize when two point clouds correspond to the same objects. We want, if we have different objects, quantify how different they are from each other. And we want to be able to transfer these reference points. Now, the reference points transfer is an application from animation, but it's also an application for many other things. For instance, at Duke, we have a lemur center. The lemur center started many lemur generations ago when it still was illegal to export lemurs from Madagascar, it no longer is. And biologists like to study these very endangered animals. For instance, one thing that's interesting is to know what their nutrition needs are for different types of locomotion in the forest. It's much easier to study that in a place like Duke, where they can instrument things, than to study that in the middle of the rainforest. And actually, the lemurs in Duke take part in many experiments. They're really part of big scientific studies. Many of them have to do with cognition. I mean, they're primates. They're not monkeys, but they're primates. They're curious, like all primates. And so they actually love these experiments. So you can see when you visit the lemur institute, you can see them sitting in front of a screen and playing with things and pushing buttons and so on. And they love those experiments. It's become very, I mean, when you do, they want to not domesticate these animals. They want to really study the animal as much as possible in its original state. I mean, but so they also don't want to stress them. So what they do is they try to, for these cognition experiments, they have taught a few hand gestures to the lemurs, so that when they need to take them to another room, they make a gesture, and the lemur, knowing that it's going to have a fun game, darts into this box, and then they can transport the box and so on. So that way they actually can do all these cognition experiments without stressing the animals. For locomotion, they need to put markers on the animal so that they can follow those and quantify exactly the movements. Which means that they have to shave a little piece of hair and put so on, and the lemurs really don't like that. So they would love to have to be able to do those experiments without having to put any markers. But that means that they should be able, from filming it from different angles, to automatically in all those frames find the reference points and track them from frame to frame. So we'd like to be able to find these correspondence points for similar surfaces. And this is interesting not just for the locomotion, but it's also going to be interesting for morphology. In practice, what morphologists do, so they have a whole collection of, let's say, teeth. We're going to talk mostly about teeth. What they do is they open their whole drawer of teeth, they look at the collection, and they have, of course, enormous domain knowledge of what they're studying. And so, by surveying this, and they see features that are present in the whole collection, and they decide on what landmarks they're going to use. So they choose something like 10, 15 points, 20, that are in common in all these samples. And then they mark them. I mean, these days that's usually done on a very high resolution virtual model on their screens. But they mark them, and so they mark landmark points on all these models. And then every surface is now represented, let's say, by a 15 tuple of 3 coordinates, so something in R45. And then they look at the distance between objects by saying, I have these 2 R45 objects. When I first scale them to scale the surface that I'm looking at to the same surface, so that, I mean, it's not the size that's important, it's the shape. So we have the same area. Then I move one so that it is as close as possible to the other. And then I look at all the distances, the sum of distances of corresponding pairs. And that gives me a distance between those two surfaces. It's called the progressive distance. And so it is something that works very well for characterizing how similar surfaces are and so on in these collections of teeth or bones that they look at. But it is something that really requires a whole lot of background knowledge in order to decide what landmarks to choose, to mark them exactly, and then after that it can be done automatically. But it's kind of tedious. And that's what Doug Boyer was interested in working with us, is could this be done automatically? Could we find a way of finding correspondences between surfaces without people having to mark these landmarks? So, because once that's possible, it would be possible to work with much larger families, much larger collections of data. And you would easily then, if you could do it automatically, you would do it for the 100 goats you have instead of for 1 or 2 or 3, and then stop because you've lost patience, because you also have to do all the mice and so on. So you would be able to get much better statistics. You would be able to do comparisons without having to have that whole domain knowledge. It takes about 3 years for graduate students in morphology to become reliable in marking things. I mean, not that they do nothing else during those 3 years, but the 3 years of absorbing of knowledge before they become reliable markers. And once they can mark it, the problem is that they can't articulate exactly what they do. I mean, they become good at it, but it's not that they can write you a list of rules. If you follow these rules, you will do it right. Okay. So it all amounts to distances between surfaces. And of course, mathematicians have come up over the years for many other purposes, for lots of ways of computing distances between surfaces. The ones that have been used for morphology typically use data points, like a progressive distance. And you want to work without data points. Now, there are also distances that don't use data points, like for instance, there is a distance, it's called the Gromov-Hausdorff distance, which is very well presented in application literature also in the last 10 years. But it turns out to be computationally heavy, and it turns out not to be very good for morphology. I mean, we tried it out. So I'm going to tell you here about some different approaches that we have done that have reasonable success. and that are based on uniformization and optimal mass transfer. Now, the uniformization, I'm going to use conformal geometry to do that. I'm not saying that I'm only using conformal maps from one surface to another, because clearly these correspondences are not going to be conformal. But we use it in order to reduce the surface to a much simpler search space. You'll see. Okay, so conformal mappings. If you take a surface in 3D, a 2D surface in 3D, immersive 3D, that inherits a geometry, and in that geometry it's a Riemann surface, and you can map that. We're looking now for a moment at surfaces without holes. So either, for instance, a chewing surface on a tooth, and that has a rim, and so that you can map to the disc, or something like a metatarsal bone, and that's sphere-like, and so you map it conformally to the sphere. The first question is already, we're going to have to compute. I mean, we're going to have to do this numerically. This theory for smooth surfaces was a theory for continuous things. How are we going to compute? And then you can, on a triangulated surface. So you can think, well, let's just do a very high quality approximation. And it turns out that, as in so many things that we have learned to do better in the last 20 years, it's better to not approximate, but actually construct something straight away, discretely, have the important features of the continuous thing that you've learned, and then construct something similar on the discrete world. We've seen this in, for instance, motion extrapolators, motion integrators in mechanics. You get a better result if you have the right symplectic geometry in these symplectic integrators, rather than just do high-order approximation. You just have to understand the problem well, and then use all that understanding in building your discrete approximation. So I'd like to show you that. It's again a little side result, but I think it's very neat. Okay, so how do I flatten? So I have a surface that looks like this, and you preserve, when you conform, you preserve angles. So I have this triangulated surface, and I want to flatten it. But if I'm going to keep the geometry, and because that's what's giving me the surface, and I want to replace every triangle by a similar triangle, then it's very easy to see that I can only make a change of scale. This thing is just too rigid. Every triangle has to be hinged with the other triangles, and you can't do it. So I have to find a way of encoding the geometry of this object that gives me a little bit more elbow room. And that is something, there are many ways, several ways in which you can perform flattening, but I like this one especially, where you encode the geometry by the mid-edge point triangles. So on every edge, let's go back here, on every triangle, I take the 3 edges, and I take the midpoint of that edge. That defines me a little green triangle. I do that with all of them. And you see, you encode the geometry of the original surface in a different collection of triangles. Every triangle, every green triangle is similar to its original triangle, because it's just scaled by a factor 2. Where 2 triangles touched, the corresponding green triangles have a vertex in common. So, but it's not as rigid now anymore. I mean, so I like to think of this as a doily, like something that you crochet and that follows the whole surface. And you could then imagine having a steam iron and holding it as one, and the whole thing has to hang together the way it's crocheted together. But some of the triangles can shrink more than others. And that way you can actually press it down and make it completely flat without. And that's really what happens. So you manage to keep the encoded geometry and make it conformal, have a different stretching and Okay, so here we actually have a little piece of surface of a lemur tooth, and this is the mid-edge-point triangles. And here you see the full. Now this is actually a tooth of a mouse lemur. So that's a little primate that's about this big. It's an nocturnal primate. So we're now looking at the second molar of a little animal that big. So it's really a tiny tooth. The way these things are scanned is they are micro-CT'd, and then from that very high resolution CT surfaces are extracted. Okay, so we have these surfaces, and we want to, since it has a rim, it can be conformally mapped to a disk. The rim of the surface gets mapped to the rim of the disk. Now, if I do my flattening with my iron like that, I'll get an irregular rim. You say, well, that's not a problem. I can map irregular contours to circles. But if you did it that way, then you would, for every tooth, you would get a different rim, and you would have to do a different remapping. And Yaron came up with a different idea, which is actually a very good idea. Instead of doing that, he said, let's take away a triangle in the middle. So now I have a hole. I have green triangles that all of a sudden have a vertex that's not touching anything else, because the green triangle will go away. That triangle I'm going to put over infinity. So I'm doing a conformal mapping where I use, just like in a continuous thing, for every point, for every little triangle, I can look at points, I can look at that one direction and their orthogonal direction, which are encoded as one. I can use that to define a complex structure, and I use that in order to map to the disk. I can do all that discretely. And I'm mapping this little triangle over infinity. Then what you get is that you have, since the missing triangle is over infinity, that the three vertices of that triangle correspond to three orphan vertices that you see at the edges here. These three. Okay, but you also had the original rim. Those also had triangles with an orphaned point. Now, what you can prove is if you really follow, if you're really faithful to building a complex structure on your triangulation, then you can prove that all these orphaned things that come from the rim all end up on one line. Which is very pretty, because it means that you've mapped your surface to the plane minus one line segment, and always the same line segment. And for that, we have a standard conformal mapping to the interior of the disk, where the line segment goes to the edge of the disk. So you have one way, regardless of what surface you started from, of always mapping your rim to that circle. And what's pretty here is that this only can work because we followed, in building the discretization, the marrow of Riemann's proof of using a complex structure. We didn't try to build an approximation. We took the essence of it and built that discretely. So there's some poetic justice in it, that giving you nice ways to do things. Anyway, you end up with a representation of the two geometries, and here, for instance, these are things from computer graphics. They have these standard models. This is the cat, and the cat has a hole in its tummy, so the cat is a disk-like surface. And if you do the conformal mappings, conformal flattenings, you find that although these two surfaces are not isometric, they look very similar. We've taken here, you look where the dots are for head and legs, for the two hind legs and the tail, and then the head and legs in the front. You see that you get the same structure on both sides. But I'm cheating a little bit, because there are different ways in which you can map conformity to the disk. And you can already see that by the fact that if you sit on the disk, there are ways of mapping the disk to itself which preserve all angles. And so if I compose one of these with one of these Möbius maps, then I will get another realization. And what that also means is that if you start from the two surfaces, it's highly unlikely that you end up in the same representation. And so things will not look like this. They will look rather like this. You will get the thing on the left and the thing on the right. They will look completely different. But if you search, then you will find that there's a way of transforming the one on the left to something that looks very much like the right. So we'll have to work with these conformal mappings, these symmetries. Okay, so we know how to compute this, and we have ways of encoding geometry on both sides. In doing this, we will have shrunk some triangles much more than others. That's what's called the conformal factor. So you have a landscape on the disk that tells you for each point how much did I have to stretch or shrink the surface in order to get there. So for my two geometries, I have these two landscapes. And what I want to do is to compare those landscapes. And for that, we're going to use optimal transport. So if I have two landscapes, this is also sometimes called, mathematicians like to call it optimal transport. Engineers like to call it the earth mover distance, which is a very much more telling way of calling, of describing it, because it really tells you I have a landscape and another landscape, and I'm trying to find a way of transforming one and the other by moving earth from sand piles to and so on, and do it as efficiently as possible. And so this is a way of saying that. What you do is you look at a way of putting a distribution on the product space of the two, so that it looks, when you project out one variable, it looks like one. You project out the other, it looks like the other. And you want there to be as little transporting as possible, so you minimize the distance. And so in order to make this work, you need to find a distance. You need to find a way of integrating. Now remember, we have to work with conformal invariants as well. And then you want to also implement all this feasibly. So, what we're going to do is we're going to introduce a distance between x and y that has the conformal distance invariant built in. And so what we do is if we take one point and another point, on each of them we'll look at a little neighborhood around it. And, well, this neighborhood you work in a hyperbolic geometry, so is going to be a little deformed, but what it means is if I put it to the center by conformal mapping, then I could take a little disk around it with a certain radius. That's its neighborhood. So I do that with each of the 2 points. If I put them in the center, I could look at the geometry around it. And now on these 2 little disks in the center, I can compare. I have to do that for positions of the disk with different angles. So that's how I compare 2 points. I look at its neighborhood in one, its neighborhood in the other, and I say how similar are these. That's going to give me a distance in which I have a conformal invariance. And then I integrate that over the 2 measures. Okay, so that's going to give you you have to be able, in order to do that, you have to approximate this conformal factor, so we can do that. You have to have expression quadrature, and you have to optimize over all these joint things with the correct marginals, but that also can be done. And we ended up with something that was kind of slow, but it gave a good idea. Another candidate distance we had was continuous process distance. So here, so what does process distance? As I told you, you take n pairs, then you move one so that the landmarks are close to the other one, and now I have coordinate pairs, and then you compute the Euclidean distance between those and 2 points. Okay. So how would we do this if we didn't much larger than the n landmarks. Hundreds, thousands of points, kind of uniform. We do that on each surface. Then we're going to have to find how to make a correspondence between these points. Okay, we distribute in a balanced way. So you have all your points. Each point will have a little zone of influence, a little Voronoi cell around it. If you had a surface of 1 and 8 points, and each Voronoi cell is about 1 over k, I map a 1 over k to a 1 over k. That means I'm looking at area preserving distances. So what we do is we say, let's take all the points on one surface. Let's look at how you can map them with an area preserving to the other surface. Let's then rotate these so that they're as close as possible to the ones here. And we now take the minimum possible about all correspondences. And you can prove that that defines a distance. And what you also can prove is that if surfaces are already very similar, then the minimizing map is going to be close to an isometry, because they're very similar. And it's also going to be close to conformal. It's actually closer to a conformal than to an isometry. So what you can do is you can find the best conformal and then move from there to an area preserving map. And so we did that, and that indeed gives you a, it gives us a true map, and it gives us a way of computing distance. So here is an illustration of the result. So, because we also had to do, before we did all this, before we found candidate distances and so on, we agreed with the biologists. I mean, something that biologists are very careful about. They design, they describe what they're going to do and what they will define as success before they do the experiment. Because it's too easy if you have too many things to fish for things that you might like. And so we had decided beforehand that this is what we would do. We would take landmarks on one surface. We would search what our algorithm would transfer them on the other surface. And then we would compare the transferred landmarks here with the landmarks that experts would have placed. And we would look at that distance. And that distance had to be small. And so indeed we did that. Here on the left you see it for teeth between primates and non-primates, for the end of a radius bone, and then for a metatarsal in a lemur and a monkey. And you see that our landmarks, they're not perfect, but they're pretty close, transfer landmarks. So that was one criterion. Another criterion was that we were going to look at the distance matrix. So we were going to look at things pairwise. We had ordered them linearly. We had 116 samples. We had ordered them linearly so that the ones that were most similar were next, closest to each other. So you have it here for the two distances that I described. We have on the top right, you have a color rendition of the distance matrix as we computed it. On the bottom left, you have a color rendition of distances as the biologists computed them. So, because things that are more similar are closer to each other in number, what we're really interested in is, and I'll come back to this, what we are really interested in is having a good result for small distances. And what that means is that we want the diagonal to look good, or the zone near the diagonal. And indeed, we find in fact that our second distance is better than our first distance, but we have the same structure near the diagonal. Now, why do I want small distances to be especially good? Because what we're doing is we're thinking of the family of all these, in this case, P's, as describing a manifold of cells, on which we have samples. Now, if you have a manifold, we have made an approximate distance. We shouldn't kid ourselves, it's a best approximation. But approximations, so think of your manifold and look at the distance between this and this point. If your manifold is like that, it's not going to be a very good thing to just compute a distance like that. But if you're very close, then the distance is probably close to what you have on the tangent plane. And that's probably close to the true distance. And it's not so bad if you have the small distances accurately and the big distances aren't. Because the small distances, if you have enough samples on your manifold, are enough to reconstruct the whole geometry. Because it's again, it's like putting little tiles on it. It's like having a complicated surface and sewing sequence on it. I mean, the sequence follow the whole surface, and you can reconstruct a good approximation to the surface from all these segments. And so, you actually, if you have small distances, right, you can use something like diffusion geometry in order to get an idea on the whole surface. Okay, so that was, then there was actually a test that we hadn't thought of, but when we saw how well it worked, the Boyer said, let's see whether it has also the same defaults as what landmarks do by people. Says, if you take the top two here, and you look at all these landmarks, then the yellow one has a natural correspondence. And in fact, this is something where experts at some point put it. Says, but then others said, we don't believe what you did here, because if you took an intermediate that is a common ancestor of both, or if you make hops over existing animals that are closer relatives, so you take smaller hops on your manifold, then you find that the yellow point ends up something somewhere else. So what it is that an entoconate was mistaken for a metastylate. And don't ask me what these terms mean, because I don't know. I'm just learning by heart. And in fact, our method is exactly the same. So when we had these results, our biological collaborators were very, very, very excited, because they had this hope that this could be done, but they hadn't thought that it really could be done. And so we had answered these mileposts. We had reached them. And so this was a paper that they were very excited. It was published in PNAS and so on. And so they now believe that we can do many things with them. In the meantime, we're thinking of extensions, we're thinking of more efficient surfaces. We also have realized that we have a very beautiful mathematical construction here. If you think of the manifold of teeth, every tooth is, but a tooth is not a point. Yes, we can think of it as an element on a manifold, but it's really a whole surface. So you have a manifold, and to each point on the surface, you have another manifold associated. You have a fiber bundle. And we have mappings from one fiber to the other. We're looking for a connection. And we want to understand that connection. And in fact, one of the things that Tingran Gao did was, in his thesis, was to actually look at this connection and use it to do very interesting things. So for instance, here what he did is, we are looking here at 3 different views of the same tooth. We're now looking at, so when you look at the connection and the manifold, you're looking at an enormous, and you digitize this by making an enormous matrix, in which you have the 4 teeth and all their points in all their coordinates. So that's one vector. And we're now going to diffuse both on the surface and to the other surfaces. We have distances in all directions. You can then look at this diffusion matrix and you can ask yourself, now if there were a good correspondence encoded in there, then what you would have is that you would have vectors, that you would have something that would diffuse locally and that would have eigenvalue almost 1. So you would have little zones that corresponded everywhere with an eigenvalue very close to 1. So you can ask yourself, if I look, because the whole thing is noisy of course, things are not exactly like that, but what you can do is you can look at vectors that are very close to eigenvectors and that are sparse, very localized. But you're not imposing that it has a representative on each of the 4 surfaces. But when you do that, you find that here I have 3 of these vectors that are very localized and with eigenvalue very close to 1. So it says that in that information encoded there is really a true mapping. Even though the diffusion could smear things out and so on, it's not doing it. I mean, it's staying nicely localized. So we are trying to learn the connection from. We have a further development, and this is something that we just started a month ago. So biologists, of course, the more you do, the grittier they become about more. So as we were showing them the results, they were excited and been used for a number of results already. We started realizing that, in fact, their landmarks, which is how we compare things, embody a lot of their domain knowledge, but not all of their domain knowledge, of course. And they actually have domain knowledge about that mapping from one surface to the next, which they encode with the landmarks. And it's only when they see a mapping that we define through our algorithms that's not exactly the right one, that then they're uneasy. I mean, that's how we saw that, in fact, they know this correspondence, even though they never articulated it that way. Because when there's one that they don't like, so now we have realized that we probably will get even better results than we have if we try to learn the connection. Now we have put it all in the connection language, the connection from that. And we can do that because if you have surfaces on which you have corresponding points, so you take their landmark points, you can build a mapping that interpolates those nicely. So we're now doing experiments where we use computer graphics algorithms for that make things correspond between one surface and the next with fixed points. And we will build the whole mapping. Then mathematician and computer scientist and biologist will sit together. And the biologist will say, oh yeah, I really, really like that mapping. And then another one will say, no, I don't. Yes, it does the right thing with my landmarks. But look, I mean, we have built, it's very easy to build software where you can take a point here and you can follow what it does on the other side. Say, look, this point shouldn't be there, it should be there. And so we'll for a test set, we'll enrich it with additional landmarks until we get the connection right. When we have the connection right for a set that they already have landmark and so on, so it's not that much work for them, we then want to learn what it is, what is the functional we should minimize in order to get a connection very similar to that connection. So we should learn not their distance matrix, we should learn their connection. And what I really like about that is that's a kind of different paradigm for learning. Instead of taking a labeled set and just asking them for labels and then try to build predictors that will give those labels, I realized what the mathematical object is that they really know things about. And we're going to build a test set that has that right mathematical object. And then we're going to learn that mathematical object. And I believe there are many situations in which, if you already know quite a bit about your problem, that kind of deeper
you have done your conformal mapping and get this landscape which characterizes it, is it then very difficult just to get only from that landscape the landmarks like the critical points or something like this, which you could easily find? And look at those?
Yeah, so in fact, when we do the second type of distance, we use that information slightly, but you see, those points do not get preserved by a Weber's map. And we have to be invariant under the Weber's maps. So the critical points are close to, but not right on top. Also, the other thing is that you only have intrinsic geometry with this whole conformal flattening. One thing that we realized with some of the teeth is that you may have so you have these cusps, but you also have valleys. Sometimes such a valley is quite sharp, and if you only look locally, then that looks the same as a maximum. And so we need to actually put in some more extrinsic information as well.
And that's also the intrinsic cost you're running.
Yeah. So we believe that we're learning the